So these questions that you were to do and have ready for class today are a review of that video that you saw yesterday. And on that video, the one thing that I would add, so if I had that parabola as my original function, again, he talked about finding the places where you have maximums and minimums, and immediately on your blue graph here, you would find that point because the derivative has to be 0. The one thing that I find helpful for that as well is making the sign diagram and say, I know that my function is decreasing then increasing. That means my derivative has to be negative and then positive. And then that matches up that this section has to be negative, this section has to be positive. The steepness of that line is somewhat a little bit, if it's a little bit off, it has to have a positive slope. You could take a specific point, draw the tangent at that point and say, I think this goes over 1, up 3, so I'll mark that point at 5, 3. But that is a judgment and an estimation. The important thing is that you see that your slope is increasing. And then for your second derivative is the derivative of your first derivative. And if we look at this, it's a straight line. What's the derivative of a straight line? Just a single number. It's just going to be the slope of that number. So your second derivative has to be positive, right? But it's going to be a flat line to represent that that slope is always the same. Check the next one, see how you did. Again, you've got your original function. I would start by finding these maximums and minimums and transferring those to x-intercepts. Once you find those x-intercepts, if you wanted to make your sign diagram, we have 1 at 0 and 1 at 4. Our original function goes up, then down, then up, which tells us our derivative is positive, then negative, then positive. So you know this section has to be positive, this section has to be positive, and this section has to be negative. Other things that are really helpful in just having a graph and sketching a graph, can you see that the original function is an x cubed graph? What's the derivative of an x cubed graph? 3x squared. This has to be an x squared graph then. And then what's the derivative of an x squared graph? This has to be an x graph, some sort of line. Again, once you've got the parabola, here is a place where we have a minimum of our parabola. So on our orange graph, we're going to have an x-intercept there. And you can do the same thing with the orange graph and say, I know that I have an x-intercept at 2. My blue graph is decreasing then increasing, so my orange graph needs to be negative then positive. Now we have the graph of the derivative, and we need to find the graph of the original. So if we have the graph of the derivative, and we know that the derivative is equal to 0 at -2, 0, and 3, we've got -2, 0, and 3 as places where we have zeros on our derivative. Since this is our derivative graph, all I can take from this section here is my derivative graph is positive, then negative in between, then positive, then negative. What does that tell me about my original graph? my original graph needs to be increasing, then decreasing, then increasing, then decreasing. What we don't know is how high these points go. How low this point goes. We don't know that. We could have this whole graph shifted up and down, and it would still be the right answer. Okay? The reason it would still be the right answer, okay, this is some theoretical stuff. Let's call my blue graph f of x. That's my original graph. And my black graph that we started with is f prime of x. What would happen if I took my blue graph and moved it up 7? I feel like 7's a lucky number. If I choose 7, you'll all understand this completely. If I chose any other number, over your head. Okay, but 7, you're going to be perfect. What's the derivative of y equals f of x plus 7? What would the graph be if I took the derivative? Well, the graph, this would still be the derivative of that. And what's the derivative of 7? 0. Adding 7 to your original function doesn't matter. So we can't be very accurate with our original graph because we don't know how much it's gone up or down. But for these kind of questions, usually they're matching questions on an exam or idea questions to ask you what's going to happen at -2. You know based on the black graph that at -2 there has to be a maximum because your derivative graph goes from positive to negative. Drawing that side diagram really helps you. But where those maximums and minimums are is a little bit of guesswork. In fact, we can't know for sure where it would be because there could have been a +7, in which case it would shift it up 7 and it would be the same shape but at a different place. So now we've got the diagram of f double prime. So f double prime is the one that we started with. On f double prime, we have a 0 here. That has to match up with something on our blue graph. But on our black graph, if we have that 0 right here, and I'm going to call it at point C since nothing's labeled here, we know that our black graph is negative here and then positive here, which means if we go back one derivative, the function before has to be decreasing, then increasing. So that tells us we need to have a parabola in blue, and at C, we need to have a minimum. Now, where that parabola is, or how wide or how narrow, is hard to tell. And then once you have your blue graph, wherever your blue graph, oh, it's going to bug people who like the alphabet. Wherever your blue graph is, well, we have two x-intercepts on our blue graph now. I'll call them A and B. My blue graph is positive, then negative, then positive, which means if I went backwards one step, my original graph had to be increasing, then decreasing, then increasing. And so I need to draw my green graph to match that. My green graph has at A and at B, comma something, a maximum and a minimum. Again, where I place those maximums and minimums is guesswork when working backwards, but it's just the general idea shape that we're looking for. Yes? So on the black, on my black equation, I noticed that my black equation is equal to 0 at, I called it C. My black equation to the left of C is below the y-axis, so that's why it's negative there. And above the y-axis, it's positive. Yes? We do have a point on the green graph. The parabola's vertex is here. Okay, that point ended up being there. Okay. What also does this point have to show up on the green graph connected to the black graph? The black graph is the second derivative. If the second derivative is equal to 0, it might be an inflection point. And in this case, it is. So what these graphs really do, and something that we're going to do at the end of class today, is we're going to go through a curve sketching review. We're sort of going to talk about what is the process if you started with an equation and were asked to sketch the curve. And there's sort of a process that you take. You find your x-intercepts and non-permissible values. Then you do your derivative and find your critical points, find where it's increasing, decreasing. Then second derivative to find inflection points. And then you're able to graph it. What these questions do is they're really testing how well do you know the overall process of curve sketching, so that if we take something from the end or from the middle, can you still work with it? Following diagram shows part of y equals f of x. The graph has a local maximum at A, where x equals -2, and a local minimum B, where x equals 6. Sketch the graph of the derivative. So again, since at A and B, the tangents would be 0, these are the key points that they're looking for on the derivative. If your derivative, and one of the things that I took from the video, and I don't know if it was video 1 or video 2 or video 3, that I didn't mind, was when they drew their number line, they just labeled beside of it, this is my number line for f prime of x. And at f prime of x, -2 and 6 is where it's equal to 0. And for f prime of x, my f prime of x graph is positive here. Between -2 and 6, it's negative. After 6, it's positive. And your sign diagram for f prime of x tells you information about increasing and decreasing. So we know that our original function, which we can see is increasing, then decreasing, then increasing. So sometimes, okay, sometimes you're given f prime of x, then you could figure out the plus, minus, plus first and draw the arrows afterwards. In this case, if I take out my eraser here, did we know the black graph? No, you just saw it because I had it on the screen when I turned it on. But the black graph is actually what we're figuring out. So I'm going to erase it temporarily. Okay? What would we have done first? We would have found out these are the flat points at -2 and 6, and you would have had those points first. Also going to erase just so the process is there. You'd have found -2 and 6 first. Did you know where the f prime is positive or negative? Not yet. What do we know? We know that our original function was increasing, decreasing, increasing. Can you see that? Original function's increasing, decreasing, increasing. And if this is the case, that tells me plus, minus, plus. Which means between -2 and 6, minus, after, plus, plus. I also know that my original shape was a cubic function, so the shape of my derivative should be a parabola. Write down the following from least to greatest. Okay? F of 0, well, f of 0 is this point right there. That's the value of f of 0. What do you know about f prime of 6? F prime of 6 is that point right there on your f prime graph. So right now I know that f of 0, the blue point, has a larger y value than f prime of 6. F double prime at -2. Okay? f double prime at negative 2. Now, we don't have the graph of negative 2 or of f double prime up here. Okay? At negative 2, which is right here. I'll change it to green. At negative 2. What can you tell me about our original function at negative 2? Can you see at negative 2 it's concave down? If at negative 2 it's concave down, we drew the cyclops. Aww. I don't know what value it is, but I know for sure at negative 2 that f double prime will be negative. Taking that into consideration, we know that that's a negative value. We know that that means that f double prime of negative 2 is the smallest because this one was a positive value, this one was 0, and this one was a negative value. That's pretty straightforward to organize from least to greatest.